Okay, let's start. Good morning. Three items before we start the class. One was I sent an email out with the feedback on how the class is going so far. And before I came here, I saw 15 responses, and thanks for the responses. If you haven't responded, let me know. So one of the problems, with this class is my impression is most of you have no background in operating systems. There are few who would like to go beyond the textbook and look at more important concepts. I'm trying to balance both of those. My primary goal is to make sure that everyone is on the same page, right? So of the 15, one person said we are going too slow and we would like to look at kernel code and look into more of the guts of the stuff, right? So my plan right now is to go through those 4 modules, the memory, file system, process, and threads, and spend the last one a little bit on security, but those are covered in other classes, but try to tie these things together. The problem is if I try to tie in how process scheduling affects memory management, we haven't really talked much about paging and everything, so I don't think you'll be able to appreciate what the interactions are till you kind of know what the paging is, till you understand what the file system says. So if you're kind of bored because you think it's going too slow from the textbook, please wait and we can get to these in the module 5 and try to tie more of them. I'll try to do a little bit of those, but I want to make sure that you understand what's going on, right? The other goal is I want you to get the big picture of what's going on, but not such a high-level big picture that you don't appreciate the problem. So for example, locks are a trivial concept, right? The real issue with the lock is not to lock the whole program, because you can solve the lock problem by locking everything and basically running it as a single-threaded application, right? But what you really want to know is how finely you should lock the stuff because of the performance issues and stuff. So I want you to get the big picture, but not such a big picture that everything is abstracted away and things look so simple, right? So, but the feedback is really good, and if you have any other comments, you don't have to do it anonymously. If you want to drop by my office, I'm more than glad to talk to you about the stuff, right? And speaking of the homework project, the next homework project is due after the spring break, right? How many of you would like a extension? Okay. So you should be aware that extension. I'm sorry. What? I can move to Friday or the next Monday, right? Huh? I'm sorry?
Can we also move the test?
Oh, test? Yeah.
It's just hard to have stuff due on the day we come back from spring break. So maybe just a few days would help out.
Yeah, either I can do it when that Friday, which is a couple of days, right? I would rather not do the Monday afterwards because we have to start the next project and stuff, right? So would Friday help?
Yeah.
Okay. The exam, it kind of fits in nicely with where the class is going. So do you really want to move it to Wednesday? Because I'm not. What?
I don't want to study blindly.
How many of you would like the exam before you go on spring break? Because I can make the spring break. I can make the exams and give it to you after class on Friday, and you can take it as a take home with the same restriction that you have, like a half an hour or whatever. If you don't have to take it, you can come back on Monday, take it. But if you'd rather do it before you go on spring break, you're free to do that too. Because I have no opinion either way, right? The only thing I ask you is, if you take the exam sooner, you're not allowed to talk about the question to others. But other than that, you're free to, yeah.
How would it work as a take-home again?
It's same exact way as it is right now. You'll have the same half an hour to write the exam. It's still open book, open notes, no searching anywhere else. You can't talk to your friends exactly like you are here, but you'll sit wherever you want and then finish the exam.
And then do we have to turn it in that same Friday, to your office or something like that?
No. So you can do it over the break or whatever, and you deliver it to me you can give it to me on the Monday at the exam time, or if you're here, whichever time, right?
Yeah, me too. I'll be on the plane.
Yeah, so it's an option. Right? I mean, it's up to you to take it either way, right? Pushing it later would mean that I have to. We cover new stuff in Monday and all those things, but this way, it's no different to me or to you, right? I mean, I'll still come on Monday. So if you want to do it on Monday, that's fine with me. So, let me do that. Let me send the stuff to you after class on Friday. And it'll include whatever we cover till Friday, right? Okay, so that's all, and the homework assignment is moved. Homework project is moved till that Friday, and yeah. So the last one is, which is not really related to this class, which is the video thing I made for this class, and this goes towards my research because. I spend a lot of time thinking about multimedia and videos and stuff, and I want to make sure that the video technologies kind of catch up to make it as useful as PowerPoint. I mean, most of us have a PowerPoint, handout stuff printed. Faculty don't think about it. It just seems so natural, and I think video is something in the future, right? Something that you would want to do. So if you have any sense of how it worked out and how, whether it didn't work out or like what would make it nicer and stuff, I'm all ears, right? This is not related to the class, but it's a more different thing. So I have a PSP here and a iPad here. You can see the video on both of those, right? So this is a good way to tell whoever buys your PSP that you're not doing this for just playing fun, but to there's educational component to it, right? Hey, the secretaries bought it. They're like, oh, because I bought this for research, right? So if you, I don't know if you want to pass it around, right? So it's a PSP, regular PSP, whatever you can get. I'm just passing it around. So, I mean, people might have seen iPod, right? So one of the nice things with iPod is it actually knows the chapter marker. So I tagged it so that you can skip to the next slide, right? The PSP lets you have to listen from start to end. But if you watch it on QuickTime or on the iPod, you can actually go to the next chapter. So you actually go to the next slides, right? So which is one of the complaints from last year where everything was in one long. You had to sit through the whole thing, and that may be a nice thing, right? That may be a interesting stuff. So whatever we did last year. Like the last year's videos and Google video and stuff, some of them are downloaded like 8,500 times, right? So I have no idea who's doing this or why they're doing this, but I want so one of the things I'm trying to do right now is to make a video on how to use a debugger, because I don't think I want to waste the class for this, but I don't want to do this over and over again. So I'm trying to see if I can put something like that, like an instructional tutorial kind of stuff, right? But I would like to know how it is used by people, because I love these things, so I kind of know how what commands and use and all those things. But I would like to see what works for you guys, right? So that said, let's dive into virtual memory, which is the next chapter, which sort of builds into your homework project in a lot of sense, right? So at this point, what we looked at is, we said that the physical memory may be too small and there are multiple processes, right? So the idea is to have a logical address space, right? Logical address space where each process gets its own address space. And we have the notion of a page table which figures out how it maps from logical to physical address, right? And we can do that either for the paging or segmentation, but essentially the idea is we kind of differentiated from what is physical memory and what your program can access. And you can have as many processes as you want. And since you have one page table per process, right, that's a nice way for you to be able to have multiple processes and have them independent, right? So logically, the next step is, since we separated the notion of what processes see and what the machines actually know as the physical and the logical address, the next step is to remove the restriction that there has to be a corresponding logical and a physical page, right? And we saw it kind of coming with the invalid bit and everything. So the idea here is your logical address, we would like the logical address to be virtually much larger than what the physical address is. And using some of the hardware stuff like the validity bit and all those things, we want to make it look like virtually you have a lot more space, even though you don't, right? So the idea here is you still have the page table, we still keep track of the mapping from logical to physical, but some of the entries may be invalid either because they're really invalid for your process, or they're invalid because the OS did some trick so that it doesn't have to find a mapping page for that. And that's the notion of virtual memory. And that kind of logically follows from what we've done so far. We're not adding new stuff, we're just tweaking whatever stuff we learned so far to get some other functionality, right? And you can do this for both paging and segmentation. So the idea here is whether you do segmentation or paging, your virtual view of the system is a lot bigger than what your physical memory is, right? And doing that gets you a lot of benefits we'll see as we move along. It gives you benefits beyond making the size bigger stuff, right? So let's look at this stuff. Here, this is the logical address space. You have a page table, right? And you have a physical stuff, right? So now we have a notion. Actually, we should have a notion of some of the storage, right? Which is typically disk, or something which is larger and cheaper, right? So we kind of move this stuff back and forth here, such that your physical page looks, your memory available seems larger than what it has to be. And the key here is we do this in such a fashion that we avoid going to this disk all the time, right? Because when you think about the memory hierarchy, this is probably 1,000,000 times slower than accessing something here, 1,000,000 or 100,000 or some large number, right? So if you have to go here all the time, your program would be excruciatingly slow. So we want to make sure that stuff is in the physical memory. Just like we are making sure that stuff are in the TLB or some other cache, we are kind of pushing it down, right? So we want to keep them as much in memory as possible. And the way we implement that is through using the validity bit we talked in the last lecture, right? So essentially, we have the same page table, right? And we have some of them pointing to stuff here, and with the validity bit set to 1. Some of them we can set the validity bit to 0, right? Where 0 may mean two things. One is there is a mapping here virtually, right, to physical page, but right now it's not there. Right now this particular page happens to be here, right, and you have to move this in, which will be done by the operating system. The process will not know anything about it except it will run slower. And there are some pages which are really invalid, and you should get a segmentation fault, right? So if you access some things, you should get a segmentation fault. If you access some other things, it's the OS which is doing the stuff, so the process will be running slower, but it won't notice a difference, right? So the OS will get involved for both of them. Both the page faults will go to the OS. So it has to keep track of what pages are really allocated and what are not allocated, and depending on what he'll do either two things, right? So here's a illustration of what that means. So you have the logical address over there, A through H, right? And the page table entries have entries for 4, 6, and 9. Everything else is invalid, right? So that means, for logical page 0, right, it's actually in physical address A. Logical page 2 is in C, and so on. Logical page 1 is invalid, right, because the invalid bit is set. But the contents P is actually in the backing store. So if you need it, we should be able to bring that contents, right? To bring the contents, we have to find some physical frame. So we need to find out which physical frame so we can move it back, which would mean that you may have to evict some of them back. So you may have to, so if it's already used by somebody, you may have to throw it. So we need to find a policy which do the page replacement, right? So for example, you may find that to bring in logical page 1, the contents P, which is in disk, I may have to throw away A, right? The logical page A, for whatever reason, whatever policies we look at. So that means first I have to figure out I need to throw out A, then I need to move in B, right? So the first half is deciding which is the page that has to be evicted. The second is deciding to actually do the I/O, right? And when you're trying to evict a page, it may be, you may just evict it if the backing store has the same content, or you may have to evict it after writing the content, right? So if somebody actually wrote into the logical address 0, the page 0, right, then the page is called dirty because whatever contents which are in the physical memory is newer than what is on the disk. So if you want to evict those pages, you may have to first write the contents to the backing store and evict them. If it was only read, it was never written back, and you have a copy in the backing store, then you can just throw them, right? So those optimizations you can do because in the most general case, you have to first figure out some victim page, some page that you want to evict, right? And you better do a good job and depending on different policies. And then you may have to write it to the disk, and then once that is written, then you read the contents that you had from that you want to move in. You read it back into the page, and then you restart the program. So the program starts to go, right? And all these operations could be slow because if you have to write, you have to wait for the write to finish, and then you have to wait for the read to finish. And some of the kernel structure that has to happen is while all this is going on, you can't allocate the page to anybody else, right? So you have to pin down those pages. So if a dirty page is being written to disk and being read in, you're not allowed to touch it for anything else. So new processors cannot use that because it's half in its stuff, right? Right. So that's the notion of virtual memory. So if you do this stuff nicely, you can build any address, any size address, depending on how big your physical address, the disk is, right? So now you can make a logical address as big as your disk, right? Can you make it bigger? And usually this is called the swap space, right? It's being swapped in and out. Can you make it bigger than your swap space?
Well, in this example, you have, it looks like you can because you have G and H in your logical memory, but those don't exist on the disk all the way over on the right.
Mm-hmm.
So I would answer yes to that question.
So yeah, in this illustration, G and H don't seem to have a backing store, right? Either because it's been allocated, but you never wrote into it, right? So there may be some tricks we can do to not put a page here, right? But if you actually used it, if you actually had any useful content, then there should be a backing store, right? There are some pages where you can avoid backing store. For example, if you have a program, right? If you have a program on disk, which is not in the swap disk, but in some other disk, right? When you're running a program, usually programs are not supposed to be modified. So if it's not being modified, then I can go back and read the program from the program disk, not necessarily from the swap disk, but those could be actually from your program, right? Which means that you're not allowed to delete your program while a program is running because it's actually using the stuff, right? You might have seen this. If you're trying Windows to delete a file which is already running, right? He'll tell you, no, you can't do that because it's actually running, right? Because that pages are being used here, so you can't just delete the file, right? Because if you move the program into the swap space, you could delete the program and move on, and that's a waste because you already have the program on disk, right? So how would you know that a page is dirty, meaning a page was written to? I think we kind of talked about it last class. Dirty bit? You're almost right? So you set the page to read only, right? You simulate dirty. So you want to know whether it's dirty, right? So you want to know if a page was written since the last time the OS cared, right? The OS always keeps track of all this stuff. So before the OS says you go, it has to somehow know something about the page, and then when it next gets control back because something happened. So remember, when the process is running, OS is not running, right? So OS has no idea what's going on in the system. So when the OS gets its chance, it sets up some things so that when the next time it gets a chance, it can go back to look at those to see what might have happened, right? So one way to do that is to set the page to be read-only, right? So before you give control to the page, you set all the pages to be read-only and give control to the process, right? So if the process ever wrote into it, they'll violate this. So you'll get a trap. The OS will get involved, right? So once the OS gets involved, it knows that somebody is trying to write, which is okay, right? So in its internal data structures, it marks that this page is dirty, and changes the permission to read write, and lets it go, right? So that way, if a page was never written, you'll never get a trap. So the OS will think it's just read only. But the moment you write something, you get the feedback. Yeah.
And do we accomplish this by adding another bit column to the page table?
That has to be provided by the hardware, right? So I think I kind of mentioned in the last class, you can have read, write, or execute only bits, right? And the way you use the read, write, and execute bits is one of these things, right? So rather than just having the valid bit, the hardware has to support a notion of a read-only page, write-only page, execute-only page, or combinations thereof, right? Right.
And all that's in the page table? Is it?
Yeah. Because so somehow you tell the hardware, and page table is the interface between the operating system and the hardware, right? So essentially, yeah. So yeah, if the hardware does not provide this, then you can't do this stuff, right? So if the hardware does not provide this, how else would you implement this? If the hardware does not provide you with the way to tell whether a page was modified, right? So what happens is, let's say this is time, right? Time is passing this way. The OS has control here, right? And it sets up a page, and then OS gets control back here, right? It gets control at these 2 points. How would it know that the page was modified? And there's no hardware support, so it has no way of knowing that, right? Yeah.
You could put a timestamp on it? Can you do that?
So you can put a timestamp here, right? How would that help you here?
You could get another time where you could compare the time down there with the previous timestamp.
So you mean the time when the page was written?
Yeah.
So if you just put a timestamp here, this will just be the time between these two, right? Which won't mean anything, right? You want a hardware where when you write something, the timestamp is updated to the time, right? Yeah. Time it was written, right? Yeah. So again, you need the hardware to help you with something, right? Either it can tell you with the fault, or it tells you by putting a timestamp somewhere, right? And actually, it is being done not as a timestamp, but we'll see how it is. It's just a counter. It doesn't have to be exactly time, right? Yeah.
You could save a checksum type value for the memory somewhere else.
Yeah. So if you magically have some space, you compute the checksum before you go, some kind of a hash, and then you compute the checksum after it's done, right? And you can figure out if the checksums are the same, whether it changed or not, right? And you might still do that because whatever checksum algorithm you have, it's still going to be faster than writing it to disk, because disk is extremely slow, right? So you can always calculate the checksum. And actually having the checksum it's pretty nice, because in this let's say there's a variable, there's a location, right, which used to have 0, right? And then you modified it to 1, and then you modified back to 0, right? If you use the hardware's mechanisms, at this point, it will be written to disk, even though nothing really changed, right? But if you use a hash mechanism, then you're really only looking to see if the contents change. If it didn't change, then you won't write it back, right? So different operating systems do different stuff depending on the hardware and what they want to accomplish, right? And once we go into the file system, the next module, we'll see how this is managed, right? I mean, in this figure, it looks like there are a bunch of blocks, right? And conceptually, this is called using a swap partition, right? Using the disk only for swap without dealing anything with the next module, right? But if you use Windows, you notice that Windows lets you create the swap file as a file, right? In which case, it has to work with whatever we'll read in the next module. So I'm going to defer it to that point. But for now, assume that somehow it goes into the disk and it's read back from the disk, right? So this is essentially the algorithm. So when the OS gets a page fault, because it's based on the validity bit, it has to know whether the page fault should really result in an invalid status, segmentation fault to the application, or whether it should bring something back. So now you have the logical page, you have the page table, you have the logical address, but you also have to have something which is OS specific, which maps this, which mirrors this, right? Which tells the OS which invalid pages are really valid but not valid right now, right? So it will have to say this particular page, even though it looks like invalid on the page table, it's really valid, right? And the actual data for this is stored right here, right? It has to have a pointer to the secondary storage, right? And say this is valid and this is valid. And for example, this page is really invalid. I mean, there is no mapping anywhere. So OS will consult this page table which it has internally and says, okay, you got a fault for this one that I can deal with. I had to move the stuff back and forth. For this page, you get a page fault. That is a real page fault. That's a real segmentation fault, and that should be exported to the application, right? So now it has to have one memory, one page at the one other page internally per process, which keeps track of all these things. And the extra entries here would say where the pages are, right? And extra entries here would say whether it's dirty or not, right? Whichever way computes those. So it's creating another table which maps this stuff. This is the OS only table. This is a table which is used by hardware, right? So the format of this table is fixed by the hardware, particular hardware. The format of this is fixed by the operating system. So it can choose whatever it wants here, but this is set by, so if you run it on Intel, it has to be in a certain fashion. You have no control over that, right? So these are the different steps in a pictorial fashion. So if you follow along on the bubble numbers, right? So the application makes a load to, tries to read memory location M, right? That's a reference, right? So if you look in the page table and that particular page is invalid, so you get a trap, right? You get the operating system involved, right? So it looks in its internal table to see what it should do. If it turns out it's actually in a backing store, it figures out what the pointer is, looks for this content, finds a free frame, right? And read the content into the free frame. If it doesn't have a free frame, it should kick some other page into the frame, and then once the frame is read, right, you'll set the page table to valid, and then restart the instruction, right? So you have to have a way of restarting instructions provided by hardware. So from a program perspective, nothing would have changed except time would have passed, right? So unless they're looking at the wall clock time, load M looks like magically all the page was right there, right? And the key here is to make sure that when you replace these frames, you do it right, because if you do it the wrong way, you can actually create a lot more page faults and your program can be really slow, right? And that's called the page replacement algorithm. So essentially, if you don't have any frames, so you have to replace some frames. You have to find a frame either from your own process or from another process and kick them out. And so the issues of fairness comes here, right? So you have to make sure that the frames are, physical memory is allocated in a nice fashion to all your processes, right? And especially when you think about threads, you have to be fair across all the threads for your process, such that you don't end up using all the physical memory to one process or the next, right? And we'll see some of those, and when you go deeper into different operating systems, they use different algorithms, and they keep constantly tweaking it, right? So one of the feedback I got from the class was, some of you mentioned that you would like to look at the kernel code and actually modify kernels and stuff, like work on kernels and change the kernels and stuff, right? I am not very comfortable with making you do that, not because I don't think it's fun, but because I think it's fun, right? Because unless you really understand what's going on, it can really turn you off, right? I promise you, I'll show you how Linux kernel is done. It's usually very simple. The code should be very simple because the kernel functionality should be well understood, right? So any operating system kernel usually is very readable because if it's very complicated, then you don't know how it works, then the whole system crashes, right? But that doesn't mean that the system is very trivial, right? I mean, there's some reason behind all the stuff. But the kicker is, if you mess up something, the only feedback you get is your machine will crash, right? You'll just reboot out of whatever you're doing, right? And there are debuggers to help you with the kernel, right? And I'm aware that many of you don't know how to use GDB, right? If you don't know how to use GDB, kernel debugging it's a whole different ballgame because you have no support system. If you mess something up, the only response you get is it'll go out of the stuff. You can read memory dumps and all those things, right? So even though some of you would like me to look into the kernel, and we'll see some of those, right? I think this class is too, it's not advanced enough to force you into that stuff, right? You can look at it as a fun stuff, but I don't want to put that to the whole class. So if you really would like to do something, I'm more than willing to work with you to explore it on your own, but I can't assign it to the whole class because I think it's, so for example, for the page fault stuff, right? Let's go back to the thing. All these data structures would be very simple to follow because basically all of them, all the stuff involves some tables, right, which has structures with a lot of elements. You fill them, you move them around, and so on. If you want to implement your own function, you may have to lock some structures at certain time, right? And you may have to fill some of these stuff at certain other times. If you mess up and don't fill up some other, if you make a small mistake, the whole system will crash. And usually, if you're not very comfortable with what the kernel does, most people hate that. I mean, most people don't like to do that, right? So that's the reason. And I think yeah. So that's that. Right? So the performance of doing this paging, right? Going back to the paging stuff, we can use a very simple algorithm calculation to figure out what it is. So if you assume a page fault rate is the rate at which the OS gets involved as P, right? Where P equals 0 means no page faults, P equals 1 means every reference is a page fault. Every instruction that you touch results in a page fault. The time for your program to run essentially is whatever time you can run whatever rate you run without the page faults, 1 minus P, times the page fault rate and the cost for each page fault, right? The cost for each page fault is you get the overhead that the kernel gets involved. You have to move some of the pages out, right? Which means that you may have to write some pages out. You may have to move the new pages in, and then you have the overhead of restart, right? And the page fault overhead and the restart overhead is not as much as the page swap overhead. And the page fault overhead would involve also looking through these tables and stuff. So, and the page swap in and swap out can be such a large proportion, essentially they dominate the whole equation. So for example, if you think of the memory access time to be 1 microsecond, and the newer processors are going towards nanoseconds, or what have you, if the 50% of them are being replaced, if you look at the equation, it's basically the first half hardly makes any difference, right? When you're touching the real memory, but the times when you touch the hard disk, which is the 10 millisecond time it takes to read some pages, pretty much dominates the equation. So you're running at the speed of how much you can bring pages in and out, right? You might have noticed it. So if you run applications which tend to be memory hogs like Adobe Photoshop or something, right? And you start those applications, you'll see your disk going wild. If you had a disk where you can hear the disk going, when you start up, you see the disk going really wild because it's kicking out a whole bunch of processes, and then your Photoshop begins to run. And then if you switch to another application, then you have a whole bunch of swapping going on. The whole system freezes, your disk will go wild while the other process is brought in, and then you go back, right? How many of you noticed cases where your system kind of looks lethargic, then it's fine, then it's lethargic and you try to switch, right? And this is essentially what is happening. And you know how painful it could be when you switch back and forth, right? And the future is we have more and more memory on the machines, and also you have applications which need more and more memory, so they kind of balance each other out, right? And the nice stuff, as we start introducing these mechanisms to do the copy, the validity bits and all those things, there are other things we can do, right? And two of them are stuff we look in the class, and one of them is copy and write. The other optimization is memory map files. To have a hardware mechanism to restart the process, and we'll start with this on the next lecture. Right?